Hello students. So in the last class we practiced rectification of curves, which basically means that we calculated the length of the arc, and we also saw that we can calculate the length of the arc for different types of curves given in different forms actually. So either you will be given y is equals to fx form, or x equals to fy form, or r is equals to f theta. So whatever the form may be, we can implement that particular type of formula to calculate the length of the arc between a certain point to a certain point. So those kind of examples we practiced, and we also saw that in what situation what kind of formula we can use. So today we'll start with basically an application side of integral calculus. So when I say application, it basically means that we will be doing some line integral, surface integral, and the volume integral. So that's the final or maybe one chapter before the final chapter. So the final chapter is basically calculating the moment of inertia and things like that, but before that we will practice this line integral, volume integral, and surface integral problems. So today we will start with the line integral. This is also motivated from the vector calculus as well. So when we go through the topics on vector calculus, we will come across the similar topics where there also we will practice line integral, surface integral, and volume integral, but that will be more towards the geared towards the vector calculus part. And today and probably in the next lecture we will look into more from the integral calculus perspective. So let's start with line integral. So line integrals. So the line integrals basically mean that a curve, so we give a small definition. So a curve in R2 is the set of points C, which is equals to all such x and y such that x equals to some phi t and y equals to some psi t, where t is lying between a to b. So for example, a circle is a curve in R2, and its equation can be given by x equals to cos t and y equals to sin t for t running between 0 to 2 pi. So that a circle is a curve which can be expressed in this form. And we say that if we assume that, let's say, and if we assume that the function f, phi, and psi are continuous and phi possesses a continuous derivative phi dash t, then integral from a to b fxy, or in fact we can write the curve actually. So the integral over the curve C fxy dx dy is equals to integral from a to b f phi t psi t times phi dash t dt. So that means basically what we are doing is we have a curve, let's say something like this, and we are basically calculating the calculating this integral of this function along this curve C. So, the name this curve is basically our curve C. So, with hit here in this definition of the curve, we can write x equals to some phi t and y equals to some psi t for a certain values of t, and we replace this the x and y in this integral on the left hand side with phi t and psi t, and this here is basically the range for t. Then this integral is equal to the integral of this function here in, of course, parameter t, and t is varying from a to b. So that's what we basically mean by the calculation of the integral of a function f along this curve C, from let's say a point t equals to a to from a point a to point b. So we have a certain point here, let's say x equals to some point, and y, and here x equals to some point, and then this will be given by that a comma b to c comma d. Then in that case, the integral of the function f along this curve from a comma b to c comma d will be given by the formula on the right hand side, where we have to express now the equation of the curve in terms of a parametric equation. So that is the main task, I would say, here, is to find the parametric equation of the curve, and based on that we can calculate the limit from where to where the t is varying, and then just substitute on the function, and then we can calculate the right hand side, and that will give us the required line integral of the function f. And next, this is somehow also motivated from the vector calculus sense, but we will work on that part when we actually look into the vector calculus part. So how do we calculate these type of integrals? So the integral calculation can be done in the following way. So let's start with our very first example. So this example says evaluate integral over the curve C dx by x plus y, where C is the curve and here we have only dx actually. So here we will have only dx, and yes, so we don't need y actually. So integral over the curve C fxy dx is equals to integral from t running from a to b, this formula here, and now dx by x plus y, where C is the curve, x equals to 80 square and y equals to 280, where 0 less than t less than 2. So we already have the parametric representation of the curve, and for that we don't need actually the calculation to calculate the parametric representation of a certain curve. This curve is basically, as we can see, it's a parabola. Because if we do y square, so since y square equals to 4a square t square, so this can be written as 4a x. So the given curve is a parabola, and since it is of standard shape, so we don't need to draw this parabola as well. Now we have our function f. The given function f is fxy equals to 1 by x plus y. So this will be actually 1 by at square plus 2at, and if I follow that formula, so we need to calculate also the phi dash t. In this sense our phi t is basically at square and psi t is 2at. So that's phi t and psi t, the two functions. So here phi t is basically at square. So from here we will have phi dash t is basically 2at, and therefore our required integral c dx by x plus y equals to t running from 0 to 2. Instead of dx we will have phi dash t dt. So, phi dash t is 2at dt divided by f of phi t psi t. So, phi t psi t is at square plus 2at. Now, this will be basically integral t running from 0 to 2. 1a will cancel out, 1t will cancel out. So, we will have a t here, 2 here, and then this will be dt by t plus 2. So, once we integrate, it will be 2 log to the base e t plus 2, and t will be at 0 and t will be at 2. So, when we substitute t equals to 2, then it will be log 4, and when we substitute t is equals to 0, then it will be log 2, and if we do some simple calculation, then it will lead to 2 log 2. So, that is to the base e. So, this is the required answer, or the evaluation of this integral along this curve C. So, that's what I mean by line integral. So, we are actually integrating along a curve. So, it's sort of like following a kind of like a line. It's not entirely a line, but the name is somehow motivated about following a certain curve. Along a certain curve, if I am walking along a certain curve, then what will be the integral of a function along that curve from a certain point to a certain point. So, that is what we mean by line integral, and this is what we are doing here. So, here in this case we have a function and we need to calculate its integral along this parabola from the point t equals to 0 to t equals to 2. So, if I substitute t equals to 0, that means 0 0. So, that means we are calculating the integral from the origin, and when I substitute t equals to 2, then it's 4a 4a. So, that means we need to calculate the integral from 0 0 to 4a. I hope it's 4a. So, yeah, 4a to 4a along that curve. So, that's what we mean by line integral here. We will work out few more examples just to make the concept a little bit clear. So, let us proceed. So, here we will have evaluate integral over the curve C x squared dx plus xy dy, right, taken along the line segment from 1 0 to 0 1. So, we have to calculate the line integral of the curve. We have to calculate the line integral of this curve taken along the line segment 1 0 and 0 1. So, first of all, let us draw this curve. So, the equation, so the line segment is 1 0 and another to the point 0 1. So, that means if I join these 2 points, let me call it as A and this one is B. So, we are basically calculating the line integral along this line segment. So, the line segment or the straight line, the line segment or the straight line joining 1 0 and 0 1 is given by, what will be the equation, is given by x plus y equals to 1. So, that means this is the equation of the straight line. So, if I put y equals to t, then in that case x will be 1 minus t. So, the parametric equation the parametric equation or we don't have to do the parametric equation here. When we are walking along this line, or let us do it anyways. The parametric equation is let's say y when x is t. So when x is t, then y will be 1 minus t. All right, where 0 less or equal to, so where t is so it would be better if we take just from the calculation point of view, you would understand what I'm trying to say. So if I take y equals to t, then x is 1 minus t, where 0 equals less or equal to t less or equal to 1. So that means when t is 0, the parametric the point is 1 0, so this point, and when t is 1, then it's 0 1, so this point, and all the other points for every value of t will lie on this straight line. So that's the parametric representation. Now let us go to this this curve. So here we have x equals to 1 minus t and y equals to t. So that's the parametric equation. So to be very precise, we can write it. This is not an equation, this is just a coordinate. So this is our parametric equation if we write it correctly. So that's basically the parametric equation. The earlier what we have written was just a point. So this is the parametric equation. Now we will integrate the function x squared dx xy dy. So first of all, we'll integrate the first term, x squared dx integral over c xy dy. All right. So we can write it as integral over c x square. I can write it as dx by dt times t dt, and integral over c xy dy by dt times dt. Now what is dx dt? Dx dt would be minus 1 and dy dt will be 1. So let us substitute the value of x square, value of x, xy, dy dt and dx dt. So this will reduce to integral t running from 0 to 1, because that is our curve, and then we have x square is 1 minus t square, then we have dt, right? So x square and then dx dt, sorry, so dx dt is minus 1, so let us write that minus 1, so there will be a minus here, and then dt, then plus xy, so 1 minus t times t, so let us write 1 minus t times t, and then dy dt is 1 and then again dt. So this will be integral t running from 0 to 1. We have minus 1 plus 2t minus t square plus t minus t square dt. So this will be t running from 0 to 1. We will have minus 2t square plus 3t minus 1 dt. So from here we can do the rest of the calculation. So you see, we substituted the value of x, which is 1 minus t, so that's what we did, and x times y, so y is t, so 1 minus t times t, and then dy dt is again 1. All right, so we substituted the value, so this will be x square is dx, so dx dt is minus of t, so minus of x square, so this is minus of 1 minus t whole square dt plus x is 1 minus t times t, 1 minus t times t dt, and then we just break this formula, so it's minus 1 plus 2t minus t square, and then this one is plus t minus t square. So if we integrate this whole thing, then we'll obtain basically whatever. So that will be the required answer. So this is how we do the line integral for this type of problem. Similarly, if we want, we can also have this curve as so if instead of this line segment, we can also be given let's say some circle. So taken along a circle x equals to cos t, instead of line segment, let me say it's a circle x equals to cos t and y equals to sin t, where t is between 0 to pi, let's say. So then in that case, you have to substitute x equals to cos t here, y equals to sin t here, and then do the similar thing. So it's just playing with what kind of curve that is given to us. So it's not that complicated. All right, we'll work out maybe one or two more examples. So let's do that. So here we have example third. Show that integral I equals to integral over the curve C x minus y whole square dx plus x minus so this one is x minus y whole square dx, and or let us take a simpler example. So instead of going straight to the complicated one, we can start with a rather simple example. So this one, integral over the curve y dx minus x dy. The reason why I'm considering this example is to show you a slight trick here, and also the statement of the problem. So that's why I'm choosing this example, because it's a little bit interesting compared to the traditional examples. So where C is the ellipse x equals to a cos t and y equals to b sin t, taken in the clockwise direction. So when we say clockwise direction, that means the seconds key in the clock, it moves, or the minute key, they move like they move in this fashion. So that's our clockwise direction, and if it rotates in the opposite direction, then it's called the anti-clockwise direction. So that means t is actually, instead of moving from 0 to 2 pi, it is moving from 2 pi to 0. And having this particular thing written here, anti-clockwise or clockwise, it plays a very important role. So you have to pay very close attention. What is the range? I mean, in which range t is varying, whether it is 0 to 1 or 1 to 0. So, I mean, of course, when we say that 1 to 0, theoretically or conceptually, it doesn't make sense, because it will always go from 0 to 1, not from 1 to 0, but it does happen. And when you actually use those limits in your integral, you may have to play with the integral to correct that limit. That means you can do 0 to 1 at some point, because you might get a minus of integral, and then you can use the formula, which is minus of integral from a to b fx dx equals to integral from b to a fx dx. So some kind of integral calculus formula implementation might be there, but you always have to play very close attention. You always have to pay very close attention to the statement, whether it says clockwise or whether it says anti-clockwise. So here in this case, it says clockwise, and that was the intention of taking this example. Now we'll see how we can solve this line integral. So to solve this, we just write I equals to integral over the curve C y dx minus of x dy, and x is given, so we can easily calculate dx dt. We just write the limit first from 2 pi to 0 because it is clockwise. Now y is b sin t, and when we do dx dt, dx by dt times dt, so dx dt will be minus of a sin t minus x will be a cos t, then b sin differentiation of sin t would be cos t. All right, and then we will have dt. So what we have done is basically we have done something like this. All right, so that's what we are doing at the moment, and then it is integral t running from 2 pi to 0 minus ab minus ab, so that everything will come outside, and then it will be sin square t plus cos square t dt. So this is basically minus of ab integral 2 pi to 0 dt. Now as I was saying, we can use some integral calculus formula to revert the limit. So it's a to b 0 to 2 pi dt, and this is the kind of correction I was talking about. So although you had higher value to lower value this in the limits, at some point you might be able to correct that, and this is what we will get. So the answer is 2ab pi. So that's actually the line integral of this function or of this integrand along this ellipse. All right. So this is what we mean here. Now we can consider a complicated example. Afterwards, we'll close this line integral chapter. So the fourth example is evaluate integral over the curve C x plus y square dx plus x square minus y dy taken in the clockwise direction along a closed curve y cube equals to x square and the line from 0 0 to 1 1. So first of all, we have a closed curve between this and this closed curve and the line this. So let us first draw the curve. So first of all, we have a closed curve between this curve and the line. So let us draw the line. So here somewhere we can have the point 1 1, and y cube equals to x square. This curve will be given by something like this. So you can look into any book how to draw this curve. So this is our y cube equals to x square, and this is our y equals to x. And since we are in the clockwise direction, so if we are in the clockwise direction, that means we are moving from this direction to this direction, and this is our closed curve. So this is our closed curve. All right. So the curve C consists of the arc OA. So let us call this point OA and the line AO. So now that we have our curve, this is our curve C. We will stop here for this problem. We will continue with a similar problem in our next class, where we see how we can evaluate this integral, and we'll So this will involve a slight how to say kind of a trick or a conceptual knowledge in a way. So we'll see that in our next class, and we'll stop here today. Thank you.